my requisite minute of promptness time, shall we say. Anyway, welcome everyone. I'm John Shin. I'm the coordinator of the stakeholder group for IDAES. It's actually a great privilege for me to have this opportunity to do so, because the IDAES team is a truly impressive team of people from multiple national laboratories and universities that have created this system that you're all taking training in today. And I get to coordinate with the people who are interested in accessing and using this system. So it's really a privilege for me. So I'm not going to waste a whole lot of your time doing anything else but saying thank you for coming to the second meeting of our tutorial. I hope you got a lot out of the first introductory session last Friday. That was kind of basics, make sure we could all get installed and learn a few basics of Pyomo. But now we're going to really get into doing things with the system. So welcome to tutorial number 2. And again, just like last week, we will be recording this, so you'll have access to it afterwards. I think that's all I need to say to introduce. Did I miss anything, Joff or Dan?
No, I think that's good. Just a reminder, if you haven't registered already, to go and register, because we will be using that to sort of distribute some materials after the video links and maybe some additional materials. So highly recommend you register.
Yeah. Thank you, Joff, for that. That's right. Again, registration is very simple. It's just a name and an email, and that's our way of keeping in touch with people who are taking the tutorial and clearly interested that much in connecting with us and learning how to use IDAES. So please do register, and this way we can keep in touch with you. All right, well, without further ado, let me pass the ball on to, I guess it's Jaffer, and lead you into the second tutorial. Go ahead, Jaffer.
Thanks, John. Good morning, everyone. Thank you for joining us today. So in the first tutorial, we briefly saw about the basics of Python, Pyomo, and a little bit of introduction of what IDAES is and how we are addressing some of the simulation and optimization disadvantages from other tools. So today the focus will be primarily on unit models within IDAES and using property packages and parameter estimation. So get my pointer here. So just some brief points before we start. So it's like a hands-on demo. If you've attended the previous one, you would have seen how Bethany walked through a Jupyter notebook. You're advised to follow along if you wish, or not. Maybe at a later time whenever you find the time, because we'll be posting videos for this. Also, if you have any questions at any point during as we are working through the notebooks, please post them to the chat, and then we'll get to it. If not, we will definitely get back to you via email to answer your questions. So as I said, the first module, we'll be looking at 2 modules. They are numbered not in series because the way we have structured our workshop folders, but the idea here is that in the first module, we'll basically be looking at the Flash unit model, and we'll be separating a benzene toluene mixture, and we'll also be using an inbuilt ideal property package within IDAES. Now, this sort of leads nicely into this module 4, which we wanted to demo actually this year at the stakeholder workshop, which was canceled. The thing is over here, a lot of interest was actually there in parameter estimation. So we'll be showing how you can actually use Pyomo's PARMEST, which is the dedicated parameter estimation tool, in conjunction with IDAES unit models and property packages to estimate certain parameters. And the example we'll be looking at today is the non-random two-liquid model. for the same benzene toluene mixture. So it's a nice segue from module 1 to module 4, and that's why we clubbed this together in this session. So the first module, with regard to any process simulation or with regard to any tool set, the one of the most important unit operations is the flash unit operation, which is more critical to show that it works well in an EO mode, because you have these set of equations that are valid only in a certain region, and then once you cross the two-phase or the phase envelopes, some of those equations become trivial. So we'll be sort of demonstrating how the flash models work in IDAES, and then also showing some capabilities towards the end for doing some post-analysis with plotting as a function of like when you change the heat duty of the flash unit. As I said, so first thing is that we'll look at how to use the inbuilt model libraries. We'll create a flow sheet object. Then we'll add the unit operation to the flow sheet. We'll set some inlet conditions and some unit level specifications. Most critically, we'll also be showing how we have built in some custom initialization routines on every unit model that you can call. And then to solve the model, we'll also show over here in this module about viewing some results and also how the phase transition is handled in EO mode. So we'll be showing how you can, with this flash unit model we have, you can transition between a single phase to a two-phase back to a single phase region. So very simple problem specification over here. You have a flash unit. It's an equimolar mixture of benzene and toluene. 1 moles per second is your feed flow rate, atmospheric pressure, and a temperature of 368 Kelvin. Just as for information, the bubble point for this mixture at this pressure is around 365, and I think the dew point is around 371.5 Kelvin. So just gives you an idea of the two-phase region. And we will assume no pressure drop in our flash unit, and also no heat duty. So we're doing an adiabatic flash over here. So let's go to the Jupyter notebook. I'm going to pull up the Anaconda PowerShell prompt. So if you had followed Keith's install instructions last time, we actually went with using Conda environment. So let's first activate the IDAES-PSE environment. So if you do a Conda env list, let me just maximize the screen. Can everyone still see my screen? Hello?
Yeah, I think they're muted. Yes, I can see it.
Yeah, okay, great.
Yeah, it's still there.
Okay, so we activate that the IDAES-PSE environment. I'm going to disable it. And you would have installed this in a folder called IDAES-PSE. And then over there, we'll be seeing the examples folder. So let's get into that. And then let's launch Jupyter Notebook, as Bethany showed last time. So this should take you to the top level directory. And then if you click on the notebook index, you will be able to see all of our modules and then some unit model tutorials and some old tutorials, which I'll sort of briefly mention towards the end of this session. So today we'll be doing the Flash unit model. So as with every notebook, we have an exercise notebook where you will have to fill in some code to complete that notebook. And then there's a solution notebook with all the completed code. So if you're stuck or if you have some bugs, you can always refer to. So as I said, I've already sort of explained about the problem specification and what is it that we're trying to do over here. But before I get on with like some, working through the notebook, some important links to like some documentation related to this module is listed over here. So for example, our main documentation page is hosted on Read the Docs. And you can find a lot of details about how we are approaching or how the core IDAES library is structured, and also some of the modeling standards we have. For example, we have some naming conventions for naming, for example, your state variables. And we have some naming conventions for, naming some of the unit model variables and so on and so forth. So if you are looking to contribute back, maybe that's something that you would have to look through. And then specifically for the IDAES unit model library, so if you click on the unit model library, you will see the list of unit models that we have. And today we'll be looking at the Flash unit. So here we'll tell you clearly what the degrees of freedom are for the units, and how do you go about in setting these. And you will get a lot more details about the internals of the Flash unit model. So the first step, is basically importing some of the PyMO components. So over here, we'll be importing the concrete model, solver factory, constraint, and value. And then from IDAES.core, we'll be importing the flowsheet block. So we'll be creating a flowsheet block within the concrete model. And then we are also importing over here the IDAES logger to sort of set the output level. So whenever we are trying to initialize, we have different levels that you can set, which can help you debug. Or if you do not want everything to be printed to your console, you can actually control that output. So, we'll look at that example as we go along. So first step, let's execute this cell. And hopefully, if there are no issues, it should basically change from a star to 1. So that cell executed without any issues. In the second cell, what we're doing is basically, we have finished our imports. And now in this cell, we are creating the concrete model object over here called M. And then on M, we are adding a flowsheet block. Over here, if you see, the argument we are passing is basically default. We're saying that this is a steady state flowsheet. Now you can set this to true if you're simulating dynamics, and there's an example in our tutorials, which you can go and check it out later. But this is basically the primary option that you will set while creating a flowsheet block object. So let's execute this cell. Now in this cell, what I'm going to show is that I think Bethany briefly mentioned when she was demoing PyMO about using pprint, and it basically prints out everything related to that particular model. So let's do a pprint on our model M. Right? So you see that right now, we don't really have any constraints, variables, nothing is being, is being added to this block. It just has a block, and the block's name is F, the size is 1, and then it has one time set. So the way we handle, because we give you the flexibility to just switch from a steady state to dynamic, when you do a dynamic to be true, this will be a time set given based on the amount of time you want to simulate. But when you do a steady state, we actually have the 0 index that needs to be there. So as we go along, you'll see a few places where I will be sort of adding a 0 index, but that only means that we are doing a steady state model. We're still doing a steady state model, but for the purposes of the same sort of platform for both dynamic and steady state, we need that time index, even though when you are doing a steady state. So once we have done this, so at this point, we have created a concrete model, we have added a flowsheet block, but there's nothing else that's added, right? So the next step is that we need a property package. Now within IDAES, we provide several property packages. So if you could, so if you go to the properties model library, you will see that we have cubic equations of state. We have the vapor liquid equilibrium property models. Specifically, we have support for an ideal vapor, ideal liquid. We have support for an NRTL liquid and a Wilson liquid. So today we'll be doing the first two. So in module 1, we'll be doing the ideal, and then in module 4, we'll be using the ideal NRTL for estimating the parameters. So over here, all we're doing is basically from IDAES.generic models. So again, from the library, there was one bug with this in the sense that we got the imports wrong. We recently updated some of our repo structure, and in that, so this should basically be properties. So from IDAES.generic models.properties.activity coefficient models, we are basically importing benzene toluene parameter block. So let's execute the cell. Then what we're doing is now at the flow sheet. So if you remember, we had the M as the concrete model, the FS was the flow sheet block. Now to the flow sheet block, we're adding a properties block, which is basically the BTX parameter block that we just imported. Now over here, we are passing some options while you're trying to build this. So over here, I'm saying that the valid phase, because over here, I know a priori that I'm actually doing a flash simulation. So I know a priori that the two phase needs to exist. So I'm saying that the valid phases are liquid and vapor. Then I'm saying that the activity coefficient model, it's ideal. So for the liquid, select ideal. And then the state vars, we provide us options to actually pick your state variables. So I think with this property model, we support two set of state variables right now. We support a total molar flow rate, temperature, pressure, and the mixed mole fraction, which is selected over here. And then there's also support for a component flow rate, temperature, and pressure. So let's execute this cell, right? Now we have added the properties, we have added a flow sheet block, we've added a properties block to it. Now the next step is basically to import a unit model. So again, if you see, we are importing from our generic models library. This is from unit models, and the properties was imported from generic models.properties. So let's execute this cell. So import Flash, and the same set of sort of sequence, right? So when we were setting up the properties, we had to pass certain options for constructing that, the same thing. So when you're adding the Flash to the flow sheet, over here, we are just saying that use the property package, which was just added right over here, right? So that's all we are going to do for the Flash. Now, so at this point, we have created the flow sheet. We have added properties. We have, sort of set the flow sheet up. So this is typically what you would do with drag and drops, or like, you just added the stuff, you've added the streams and stuff, right? Now, what we need to do is.
Can I ask a quick question? In case someone else is running into this, I'm getting on line 5, no module name, IDAES.generic models.property models.
Yeah, so that's why I was over here, right? So there was a bug with it. Yeah. So when you simulate that, just change that to properties. It's not properties underscore models.
Sorry, I missed that. Okay, thanks.
Yeah, no worries, no worries. Did that work?
Sorry, yes, it did.
Okay, great. Was it Miles?
Yes.
Yeah.
Yeah, sorry, right. Trying to have side conversations. I shouldn't be doing that.
Yeah, no worries.
Okay. Mine didn't work. I still get an error that it doesn't find properties models now. Same error, but.
Oh, wait, you need to change that from property models to properties. So it should be from.
Yes, that's what I have, properties, and it still gives the same error. Now it says it doesn't have properties models.
Quick question, did this cell work from IDAES.logger?
It does work for me.
So one,
It works for me.
yeah, what's it? Huh.
So two things could be happening. One is that if you were using environments, you wouldn't activate the environment. However, if this cell executed, then that means that you have the right environment. So that's why I'm asking if the IDAES logger import worked.
you
Yes,
copy-
mine looks the same as yours.
Could you copy the error message in the chat window so we could look at it, please?
Okay.
Anyone else having issues? Well, I'm also glad that quite a few of you are working along, so that's great. Andrew, did you get anything on the chat window? Or should I go along?
Not yet. You've got properties underscore models. Remove the underscore models after properties.
Properties dot models or just properties?
Just properties, then dot activity coef
okay.
models.
Yeah.
There we go. Oh no, wait.
Okay, great. Okay.
Wait, Jaffa.
Oh,
No, I think that's okay. Let's see. Well, I guess it's okay. It didn't do anything. Didn't give an error.
yeah. So meaning that if this over here, if it executed without anything output, then it worked.
Okay, thank you.
Yeah. Okay. So now one of the important things you have to sort of like, you know, it's useful to know is that how many inputs do you need to specify for the model, right? So let's import a utility function that we have basically that helps you find the degrees of freedom on existing on a unit model or on a flow sheet and stuff. So from over here, we'll be saying from IDAES.core.u2. So a useful tip in Jupyter Notebook is that if you do a tab, it will sort of show an autocomplete feature. So you can do, so we need to import from model statistics, import degrees, and then I just, oh, sorry. So I press tab and then it autocompletes for me, right? And then let's call the Python help function on this utility method, right? So over here, once you do a help on that, it basically shows you what this module does or this method does. Over here, just method to return the degrees of freedom of a model, and then you just pass the model to be studied, right? So let's do that. So let's print the degrees right? So you should see 7 degrees of freedom when you execute this on the model M that we just constructed, meaning that we have to provide 7 inputs to make this a square problem, right? Now, if you remember, I said that we have, so let's just try to walk through what these 7 variables are, right? So we have, it's a binary, it's a 2-component system, and the state variables we chose was total flow rate, temperature, pressure, and the mole fraction, right? So if it's a 2-component system, you need to specify mole fractions for 2 components, so that makes it 5. And then you have two unit model level specifications. And if you remember over here, if you could, so if you go to the documentation, we tell you that, if you you need to specify either the heat duty or an outlet temperature or the delta P, right? So let's go back over here. Right, so over here, what we're doing is basically trying to fix the inlets. So it was 1 moles per second, 368 Kelvin, atmospheric pressure, and then the mole fraction for the two components, right? And then let's fix the unit level specifications, which is basically your heat duty. We fix that to 0. And then we also fix our delta P to be 0. So over here, we are also showing you what those names are. So just use that. Right? So you execute this cell, and you shouldn't see any output. Now let's again check the degrees of freedom, right? So, for the sake of time, I'm just going to copy paste this code over here. Right? So now you see that the degrees of freedom are 0. So we fixed our inlet, all the state variables that we chose, and then the unit level specification. So now we are good to go, and then we are ready to simulate. So we have set up the flow sheet, added the added properties, unit model, set the inputs and everything. So we're good. Now, this is one.
I'm getting I'm getting an error for there's no delta P attribute.
It's on Flash, so you should be saying m.fs.
Oh, okay.
Flash.
Thank you. Good.
Yeah.
Got it.
Right, because it exists on the unit model, right? So.
Right. No, I just missed that. Okay.
Yeah. All right. So now.
Question. Why do we need to specify both the mole fractions? Shouldn't one be enough?
That depends on how you write your property package, right? So if I had a sum mole fraction is equal to 1 constraint at the inlet, then what you're saying is correct, right? But if I didn't have that, so we don't write that at the inlets. At the inlets, we expect the user to sort of, specify all the state variables that they chose.
So to clarify that a little bit further, it's because the inlet to the unit doesn't know that it is the feed to the actual process. So the inlet to any unit generally expects that there will be an incoming stream attached to it. And because of the way PyMO and IDAES works, that stream will contain all the mole fractions. Thus, the inlet can't have the sum of mole fractions constraint, which leads to this unusual case that when it's the actual feed to the process, you do need to specify both mole fractions. When we're doing an actual flow sheet, we do have a feed block that lets you specify only one of the mole fractions and has the sum of mole fraction constraints.
Right, yeah.
And if it doesn't add up to 1, will it throw an error, or it's a user has to make it sure that it's 1?
It will take whatever values you gave and effectively end up, well, it will use them for whatever that ends up being in your result.
So there's nothing stopping you from saying 0.5 and 0.6.
Yeah. Unfortunately, there's a lot of the caveat of user beware with some of these features, just because to give you the flexibility to do a lot of the things we designed IDAES to do, there has to be the caveat that you have to be careful not to get yourself into trouble.
if you put 0.5, 0.6, what's going to happen is it won't normalize, or will there be an error?
It will effectively end up normalizing it. You'll probably
Okay.
find that your outlet flow rate is larger than your inlet flow rate in terms of total flow. But the component flow rates at the inlet and outlet will be the same.
All right. So the next step, we're going to be initializing this unit, right? And over here, if you notice, I'm actually passing an argument that's setting the output level. And now over here, I'm going to be setting it at info, and I'll show you some other logger levels for this step. Right? So you're seeing a lot of output being printed, and you're seeing what's happening in these steps. Now, what you could also do is, let me just show you over here. So if you go and check out our documentation, we provide different logger levels. So right now we set it at info, right? So if you set it at debug, it will basically throw everything that's happening under the hood out, so that you can actually see every solves that are happening as part of the initialization step. Now, if you set it to, let's say, info low or maybe warning, you are going to be restricting the output. So let's try. Right, so I changed, right? And you saw that nothing was printed out. The reason being that there was no warning messages that were captured, and so there's nothing that's being printed out. And if I do info high, you're going to be seeing a bit more information. And when I set it to debug, you will actually see all the solver outputs as well. So that's just a useful tip when you're using IDAES to help you debug as you go along. Right. So the next step is basically, now we just create a solver. So Bethany briefly showed you how to do that in the last one, but we'll be selecting IP opt. And let's solve this model, right? So solve. And then I'm going to be setting the solver output. I would like to see the solver output over here. Right, so you should be seeing, so one, Bethany pointed to this, but let me just reiterate. So over here, just every time you solve in EO mode, if you're thinking that you're solving a square problem, it's always good practice to go look at this, and just to be sure that you're solving a square problem, or you see the same number of degrees of freedom that you expected that you have. So that's that. And then the optimal solution, the solver output is clean. And now let's look at the results, right? So over here, all we're doing is that just printing the vapor outlet pressure. So vapor outlet and liquid outlets are basically ports on our flash units. So if we execute the cell, you will basically be seeing the vapor outlet port and then a liquid outlet port. And you'll see that the pressure is the same. It was an adiabatic flash, temperatures are the same, but you will see that the vapor outlet flow rate is about 0.39. Liquid outlet is around 0.60 with the corresponding mole fractions in those streams.
Hi, Jeffrey.
Now,
can you go back? Can I see the commands, because I'm getting some errors?
Oh yeah, sure.
Okay, thank you.
Yeah. All right. So now this is directly using the display options that we have on PyMO components. So we are using that on the port. So we're basically displaying what is contained in that port, and that will typically be your state variables. right? Now, however, within IDAES, we've also built in some report options for unit models that you can sort of use, and that basically generates a nice stream table and the critical or the important unit level specification. So for a Flash, it will basically show you your heat duty and pressure change. Remember that we fixed this, so it should be under fixed, it will be true, right? And stream table, it will show your inlets, your vapor outlet, liquid outlet. So it basically presents a very nice report on the Flash unit model. So that's basically the first half, where we have sort of just put together a Flash unit model, simulated a very simple case, you know, in the two-phase region. So in the next, so any questions at this point? Is everyone able to sort of get to this point, whoever we're working along?
No, I got a bunch of errors again. So I didn't get past line 26.
I'm not sure. Is that the solver or the initialize?
That's just the properties.
Oh. So the inputs?
M.fs properties, it gives a warning, and then nothing beyond that works.
What is the warning?
Yeah, what's the warning?
Implicitly replacing the component attributes properties, blah, blah, blah. So it's like,
Okay.
Okay. What I would recommend is that on this cell, maybe restart and clear output. So, Andrew,
Yeah,
is that the best way, right?
Clear. It sounds like you've executed the cell twice or something, and
yep,
the risk. It's an issue with Jupyter Notebook that it executes cells as you execute them, so it's possible to get yourself into loops. Just clear all and try running everything through again.
okay.
So, so on the cell where you're seeing the warning, click on that cell and then go to kernel, restart and clear output, right? And once you've done that,
Cell, then
and
run.
then come to cell and then run all above, and then execute the cell once, so you will not get this warning. What happens is that you know, you've just run the cell. Oh yeah, I see what happened, because you're getting the wrong inputs and then you executed this and then you chain the inputs and you execute it again.
Okay. No, looks like it worked now.
Okay.
Show the
And
solver arguments one more time.
yeah, the solver setup or over here?
Yeah, the solver factory. The two
Yep.
left there. Thank you.
Yeah, no worries. Okay, so in the interest of time, let's move along. So here in this exercise, what we basically be doing is basically plotting the vapor flow rate versus the heat duty that we set for the Flash tank. We'll be increasing the heat duty from minus 17,000 joules per second to about 25,000 joules per second over 50 steps, right? So we will be using the Python's NumPy package to create the range. So over here, we'll just import NumPy and P, right? And then over here, we will need to create a for loop, basically to just run several cases by setting a Flash, by setting the heat duty to one particular value. So over here, we will be saying for duty in np dot space start values 17,000 and values 25,000 over 50 steps, right? I'm going to wait for a minute for everyone to sort of fill this pieces up. So this piece and this piece. Also, Andrew, Bethany, if you find any typos, please point out. Right, so over here you see what we're doing, right? So we are basically looping through this range, and then over here we are basically fixing the heat duty to that particular value, whatever that is right now. Then we will be simulating that flash unit and storing the results in a list so that we can plot it later, right? So hopefully I didn't have any typos, but let's see. Right, so you should see an output like this. Oh, didn't like plot.
Forgot to execute the line above.
The cell above.
Oh, thank you.
So you just reset there. I made the same mistake you did and didn't run the plot. Why are you reset?
Yeah.
Why can't you just rerun it?
I will briefly talk about that. I had a nice trick, but let me just run this. So everyone should be seeing this plot, right? So so what happened was basically that if you remember that I executed this cell, right? And my starting point, if you notice that over here, I didn't initialize the model over here. So if you look over here, I'm straight away just solving it because my previous stop point was actually a solved model. You know, it was a good initial point. Now then I went from minus 17,000 all the way up to 25,000, right? And then that's the last loaded up results point for the flash unit. And when I ran the cell again, it's basically starting off from the extreme point rather than a good initial point. So that's why that first step was failing, Miles. And we'll see that again in the next step, where sometimes you might need to initialize, sometimes you might not. You could use that previous point and go on, but it all depends on where you are. Because right now, if you are at 25,000 joules per second, you are all the way in the vapor phase, right? And when you executed the cell again, you were trying to solve this point over here, which is minus 17,000, which is all down in the liquid phase. So it's not really a good starting point. The previous starting point was somewhere over here, right?
Mm-hmm.
So that's basically what happened.
The good news is I ran it anyways, and it actually solved. It just took a while.
Yeah, but if you look at the solver output, the solves aren't going to be that clean, so which is always an issue. So.
Okay.
Okay, so in the next cell, let's do the same thing, but let's just plot the mole fraction of benzene in the vapor phase. Right, so all I'm going to do is basically right. Create an empty list again. Now, I'm going to show exactly what I just talked about or what we saw. So the only thing that we'll need to change over here is that we will be, instead of plotting the vapor flow rate, we want to plot the mole fraction of benzene in the vapor stream. So And then let's say, right now, so this should basically, the first step should basically fail. The reason being, again, as I just mentioned, that the last point of sol over here is the 25,000 joules per second point. And then if I don't initialize again back from a reasonable point, that first step of minus 17,000 will fail away. So if you see that, so it'll sort of do that, but then that first step will fail, and we will be seeing like a nice plot. So what we should do is do this. So let's just give a reasonable starting point. So let's initialize this model again. So if you remember, this is that same simulation sort of point we had. Very many typos. Okay, let's execute that cell again.
Is there something different about initializing? Like, I guess I'm not understanding how initialize works versus just solving. When you're initializing, what is there like? It's pulling from some parameters it's got somewhere that's saying those are initial conditions or something?
No. So when we talk about initializing for these nonlinear system of equations, is that first thing is that a good initial guess for your variables, that's one thing, right? So that's always tricky. Or the other way to do this is basically following this concept of modeling hierarchy. So the classic example is that if you're trying to solve a plug flow reactor, which is non-isothermal, and so you don't straight away start solving that, but you solve like an adiabatic PFR, just the mass balance equations. Then you use those initial points as initial guesses when you're solving for the PFR model with an energy balance. And then you solve the final step, which is the non-isothermal, non-adiabatic PFR. So that's like the concept of modeling hierarchy, which is what we basically do in the background. So in the background, what we are doing is when we say initialize, we are going and initializing your state blocks first. Then we will initialize the outlet state block at a reasonable condition. Then we will initialize that entire unit model with whatever unit level specifications you do. So that last step in initialize is actually already a solve, but we're just resolving the model from that last point when we're doing that solver.solve, right? So this is what I think is one of the like really cool features in IDAES, is that most of our unit models or property packages, there are custom initialization routines that actually work well. And at the same time, you can go and change that routine if it doesn't really work for your system that you're trying to model. So
what, I guess, yeah, maybe it's just part of the art here, but why don't you just naturally initialize every solve? Is there some benefit to breaking it up to have the user manually initialize and then solve?
I'm not sure I got that question.
Like when we run the solve later, why not just have it embedded in the solve process? I guess is there some? I guess I'm not catching the nuance.
Because the solve, when we call it, is actually just a direct pass to a external solver through the PyAMO interface. So it's just saying, take this problem matrix and do whatever the solver does to find a solution. But because these are nonlinear problems, if you don't have a good set of initial values in that matrix that you send to the solver, it will probably fail. So the initialize method is a method we've built to try to get those initial guesses. In a lot of cases, the initialize is actually doing a lot of smaller solves.
Right.
Yeah.
No, I get that. I guess the subtlety of my question was along the lines of you could embed that initialize method into the solve, right, to pre-initialize, but maybe there's some advantage here of speed. It seems to me like you're, in this particular case, we're looping through duty, and so you know that it's going to be in an okay spot for the next iteration. So why waste the time initializing type of thing? Is that kind of the right idea?
It's more that the solve that you're seeing there is a PyOmo command, not an IDAES command. That's the base PyOmo command to pass this problem to a solver.
Right. Okay. That's the key, is that you're using a different pack. I see.
Yeah.
You
try not to re-implement PyOmo.
Got it. Okay.
So Miles, another follow-up to that is basically that let's assume that you want to initialize a model, but when you initialize, it's always good to initialize with a square problem, right? And once I've initialized my Flash, when I'm solving, I can unfix heat duty, or I can basically say, okay, maximize purity of benzene in my vapor stream, unfix heat duty, and now I'm solving an optimization problem, which I then pass on to solve, right? Even when I'm doing that, passing a good initialized model is critical for ensuring solver convergence. So for that reason, we don't really embed that together, right? I see what you're getting at. Technically, if you're just solving a square problem, that last step of initialize is actually a solve on the model itself.
Mm-hmm. Okay.
Right. So, okay. So the last step. So one of the advantages of the equation-oriented mode is that you can also set what your outputs are, right? So not just, so here we specified inputs. These are the classic things you say. You specify an input, you specify your heat duty, your delta P. Now, what we will do over here is basically we will unfix the heat duty. So now we have 1 degree of freedom, and let's fix that we want the outlet mole fraction of benzene in the vapor stream to be 0.6, right? So let's just add a constraint. So that's the mole fraction of benzene in the vapor stream. We fix that to 0.6, right? And let's see if this works. So if you notice, we are still solving a square problem, 42 variables, 42 constraints. And then the heat duty that we need, if we want the mole fraction of benzene in the vapor stream to be 0.6, is basically 5,083 joules per second. So this is sort of like an example where, the advantages of using equation-oriented modeling approach, where if you want the outlet to be a certain condition, you can fix that straight away, and then you can unfix some of your inputs to figure out what that input should be. So hope that was useful, and you will find more information in our documentation if you're interested as to how we are doing these smooth Flash formulation. The cool thing is that over here, we are able to transition from a single phase region to a 2-phase region and back to a single phase region. So how we are doing that, you can actually check out some of our papers on our website. You can find the links on our website. So if there are any other questions on that, please feel free to email us. Okay, so let's quickly move to the next one.
I have a really quick question. I was trying to find, you might have mentioned it, and I was trying to find it in the text, but didn't. But what does the 0 represent in the benzene, the mole frac comp?
Oh, that's the time index.
Time, okay, got it.
Yeah. Okay, so in this, whatever we just did, in that module, we looked at using an ideal gas and an ideal liquid for the property package, right? So now if we can, in this module, we'll be just switching that to where we'll be selecting the activity coefficient model to be NRTL. Now, the NRTL model, you need to compute your activity coefficients, and the equation is, so the equation is like shown over here. Now, in this equation, this are NRTL model parameters. So one is your alpha is your non-randomness parameter, and then tau is basically your binary interaction parameter, right? So both, if you notice, are indexed by the component, the number of components. So you have an alpha ij, so that means that you will have n times n number of variables. So if you have a 2-component system, you will have like 4 variables just for this alpha. And then if you have, again, like the same goes for the binary interaction parameter. Now, if you look at the original paper, you will actually see some recommended values for the non-randomness parameter depending upon the liquid mixtures. So for the purposes of this example, we'll be using an alpha value of 0.3. What we will estimate for the benzene toluene mixture is basically the binary interaction parameter by using like about a data set with about 50 data points where we've generated the mole fraction of benzene and benzene in the vapor and the liquid phase as a function of temperature, right? So now just a quick, not really relevant for this sort of like the module to be done, but something if you want to work on yourself later on after we have done. So for the parameter estimation module, we have 2 modules, and I'll sort of briefly explain why. Over here is that, so this is basically the structure of an IDAES unit model. So you have the unit model block within which lies your performance equations, and then you have your control volume block, which basically writes your mass, energy, and momentum balances, on which we have your inlet state blocks and an outlet state block. But both of these state blocks take their parameters from this properties parameters block, where our parameters to be estimated reside, right? Now, if I want to use, so there are 2 approaches to sort of estimate parameters that are associated with some property package. One is to use just in conjunction with a unit model, but given the block hierarchical structure and then the advantages of of IDAES being built using that block structure, you can basically just use a state block in a flow sheet and then attach a parameters block and then just use that for your parameter estimation if you don't really need a unit model. Now, today we will be looking at the approach 1 because it was a nice sort of a lead from the module 1 that we just did. We will still be using the Flash unit model, but then there's also the approach 2 Jupyter notebook that's available. So if you go to the index, so if you go to the index over here, you can actually see that there are, for the module 4, there are 2 notebooks. One is using the unit model blocks, which we'll be doing right now, but there's also one using the state blocks. And towards the end, I'll briefly show what's the difference between the 2, but you should get the same results from the 2. So let's do the using the Flash unit model. So over here, it's going to be pretty simple. So we'll be using the Pyomos ParMS tool, which is the dedicated parameter estimation tool. And that tool basically requires like sort of like 4 things for you to use that tool. So we'll need to set up a method or a Python function that returns an initialized model. We will need to define the sum of squared errors. We will need to define what are the variables that we're trying to estimate, and then we just call the parameter estimation tool on that. So over here, what we're going to do is that quickly just do the same thing that we did from the previous thing. So this will be very familiar. So from Pyomo.environ, so we'll import concrete model. then the same thing, then from IDAES.core, import flowsheet block, and we import the unit model, generic models dot unit models Flash, right? So let's keep it so. Now, if you see in the next cell, all I'm doing is the same thing where over here you wouldn't have any problem. So here we had the right import, so it's properties. So we are doing the same thing where we're importing the BTX parameter block from the generic models and properties, and then I'm also importing the logger function. Then the next cell is basically where I import Pyomo's parmes tool. So that's in pyomo.contrib.parmes. We'll import that. And then we are also importing the pandas package because we'll be passing the data set and using the pandas data frame. So that didn't look good. Okay, know what that glitch was, but that cell, those imports are now done, right? So in the next step is that we are basically writing this Python function or a method to return an initialized model. So what we're doing over here is that we will be creating the concrete model object. So this will be very similar to what you just did in module 1. Then we create the flowsheet block. So then we pass the options. And we create the properties. Now, if you see over here, the options, last time we basically had 2 options that we selected. One was the valid face, right? So we say that still liquid wrap, right? And then second option is your activity coefficient model. And last time we selected ideal. Over here now we're saying NRTL. Right, so that's done. Then we create this Flash unit model. We pass these properties. We are initializing at a certain inlet condition. So I'm selecting the same inlet conditions we had, same Flash unit specifications. Now, keep in mind that at this point, if we had selected an ideal, this would have been 7 degrees of freedom, and we would have been, at this point, we would be 0 degrees of freedom. However, we selected NRTL property package. Now, because of that, as I said earlier, that we will be having about 8 more degrees of freedom, 4 for the alpha and 4 for the tau. Now, for the alpha, we will be fixing that at 0.3 for the benzene toluene and then the toluene benzene. And for the benzene and toluene, we'll be setting that to 0. Now, these are the parameters that we'll be estimating in this example, which is your binary interaction parameter between benzene toluene and then the binary interaction parameter between toluene and benzene. So these initial values are being set, and the only reason I'm doing this over here is to basically initialize this model with 0 degrees of freedom. So when you're initializing, it's always advisable to have a square problem. as I said, the data set that we have that we'll be using is basically a function of temperature, right? So for the initialization purposes, I initialize at a temperature of 368 Kelvin. But once I've initialized, now I'm fixing the temperature of whatever the actual data set point is. And then I'm actually setting some bounds for my variables that I'm going to estimate. So I'm setting the lower bound over here. You can do that using the set LB function, which is I'm setting bounds for both from -5 to +5. And all I'm doing over here is just returning this M, right? So this is sort of required when you're using the PowerMesh tool. So this is one of the first requirements. So hopefully that should work because I didn't really call that model. So we won't know of any errors until I actually call this. Now here's basically what we'll be doing over here. So as I said, the second thing that we need to do is pass a list with the variable names that we are going to estimate. So in our case, this was fs dot and
Do you want those to be double quotes or single quotes?
it could be double or single. Yeah, it
doesn't matter. Okay.
Yeah.
In Python, either work as long as they're matched.
But Jaffer, I think.
But in this case, in this case, it's going to recognize that you already had a double quotes, and this is going to recognize that's the end of the string. Yeah, thanks,
Right,
Bethany.
that's what I was thinking.
Okay. So
I think you're still missing.
You're
one
missing
quote.
a double quote, yeah, right there. For the comma.
okay. So
For the comma, you're missing a double quote. Or yeah, right above, up one, just straight up from there.
oh yeah. Thanks. So that worked. Then over here, we will be loading this data set. So this data set has about 50 data points. And if you display that, you will see that this is basically the mole fraction of benzene in the liquid and vapor phase as a function of temperature. So we have about 50 data points. And then in this step, this is going to take a while, but hopefully, we will be creating again a method to return the sum of squared errors that we will be passing to the PowerMesh tool. So over here, because this is we are trying to estimate the parameter, our objective function is minimize sum of squared errors. And over here, we're trying to minimize the error between the mole fraction of benzene in the vapor and the liquid phases, right? So let's figure out. So this one is basically that data that's coming in, right? And then over here, I am basically subtracting from the flash vapor outlet stream the mole fraction of benzene. So this is one term. Let's see how many typos I have in this. So liquid. Well, hopefully that is right. And do anyone see any typos over there? So what we're trying to do is basically subtract benzene from the vapor outlet benzene, square that term, and then we have this, square that term, and then add the two. Yep, that's all right. So over here, if you notice, I multiplied this expression or this sum of squared errors expression by a factor of 10 power 4. And the reason we're doing that is because that this SSE will be an extremely small number, right? And given that this is the difference between mole fraction in that expression. So we need to scale that objective, and IP opt, you know, we will, it doesn't scale up. So we will be scaling it up so that we get a good solve and good convergence when you're solving the parameter estimation problem. So that's done, hopefully. Now in this step, all we're doing is, yeah.
I was going to say, what about a method of like dividing by, well, actually, I don't know what this is going to look like exactly. Divided by some parameter to make it, I mean, like, what is the goal there? Is it to get it to near like 1, or what kind of magnitude?
Yeah, correct. So the magnitude, so this one was actually of the magnitude about 10 power minus 4, or I think 10 power minus 5. So what it was to bring it closer to like around 1 or 10, or to the order of 10.
Okay.
Okay, so over here, all we're doing is basically from creating the parameter estimator object. So you notice that it takes 4 inputs. So first is that model or the method that returns an initialized model, which was what we created in the very first 3 cells. Then the data set, which was our pandas data frame. Then the list of the variable names that we are going to estimate. And then the method that was basically to compute the sum of squared errors. And then we set t is equal to true to look at the solver output. So hopefully this should work. I'm just double checking the SSE. Okay, let's see. So this takes some time because we have 50 data points, and so the star basically shows that it's still running. If you want to see some outputs being printed as things are going on, we could have set the IDAES logger levels in our initialized model to sort of like info, and then it will just basically keep printing it out every time that's being initialized, so that you know that things are working. In hindsight, I should have done that over here, but hopefully that works, and then we can see the value. So in the meantime, any questions up until this point? I do have only one more. Ah, my bad. So I had made a mistake with the variable names, and it was just repeating. So that's why I was just saying 1 degree of freedom. And Well, let's try a second time. So while this goes on, this is the other notebook that I talked about, which basically just demonstrates the approach 2. And okay, so this one's finished solving. So over here, you see, oh wait, can everyone see my screen?
Yes.
Okay. So here you see that we had a total of 2,952 variables and 2,950 constraints. So basically 2 degrees of freedom, which are your 2 parameters that you're trying to estimate. And the solve is done, optimal solution found. Let's look at the values. So if you look at the values, you can see that the benzene toluene binary interaction parameter is estimated to be 0.478. And then for toluene benzene, it's minus 0.409, right? And the SSE over here is 0.00463. So this is a brief example for using parameter estimation or the Pyomo SparMesh tool with the IDAES unit models. And this is like another example where we built a IDAES on top of Pyomo, so you have access to a lot of the features of Pyomo. And at the same time, we also used the Pandas data frame to pass the data set and to process the data. Over here, the next step is basically an advanced option that SparMesh provides. So it's like basically the bootstrapping tool where you can repeat the parameter estimation over n samples. And this basically does some resampling of the original data set. Now, in the interest of time, I'm just going to run like about 4 runs over here instead of 10, right? All it's going to do is that we had 50 data points. It's going to run 4 different parameter estimation problems, but resampling the data points from that data set. And there could be some repeated data points because obviously we're not taking a subset of it. We're still taking 50, but there's going to be some repetition, right? So this sort of helps you identify the confidence regions around each parameter estimate. More useful when you're trying to estimate with some pilot plant data or some lab data or some actual plant data. Over here, the data set is like simulated data set, so you're not going to see a lot of variation, but let's look at that. Now, while this is running, I'm just going to quickly just show the results while we are using both the approaches. So with the first approach, which I just showed, we used the unit model with the property package, and then you see that we had 2,952 variables, 2,950 constraints, and then the objective function was so much, and then the parameters were estimated to be that. And when you're using a state block approach, the only difference is that you're solving a much smaller problem because you don't have a lot of the unit model level equations now, or the unit model level variables. All you have is your property package equations and variables along with your parameters that you're trying to estimate. And obviously, it's expected that you see the same results using both the approaches, but it also shows the flexibility we have with the IDAES, right? So you can basically not use a particular block, and it's not necessary that you have a rigid structure. You can basically use it for whatever needs that you have. And then you can use approach 2 because it's more robust given that you're solving a smaller problem. And if you have a large data set, then it might be advisable to use this. But this only works when your parameters are associated with your property pack. And they're not really dependent on some unit model level performance equations or something like that. So that was So the bootstrap is still running, but I think we can open the floor for any questions or some feedback, comments, or anything. So that brings us to the end of module 4, and hopefully you'll be able to see the results before we sign off.
I have a question. I'm using the online document to download this example, but there's no module 4.
Oh, so we recommend you look at the new install instructions. So if you missed the first tutorial, let me just go there. So this was like a patch release, so you wouldn't get that in the standard release. So one sec. So go to news and events on IDAES.org and check out these install demo speaker notes and the video link as to how to get the module 4.
Okay, thank you.
Yeah.
Hi, Jafar. Thank you very much. This is wonderful, very powerful tool, and I think I can use it a lot. I have a question about this parameter estimation. Here we use NRTL. Can I do the same thing for cubic state of equations?
Yes.
Estimating the parameters?
Yes. I'm trying to rephrase the question because the audio was pretty bad. The question was, we estimated the parameters for the NRTL, but can we do that using a cubic EOS? Is that correct? Did I lose? Andrew, do we have any questions in the chat?
Not at this point.
Okay, so this one we've run the bootstrapping example. Yeah.
Are you able to hear me? Okay, so on that, one more question. So we use this benzene toluene property package right from the box. Is it possible that I can create my own? Is there an example available where I can create my own components and thermodynamic methods to be used?
Right now we don't have an like an example or a Jupyter notebook like this, but there's been sufficient interest from quite a few people to sort of put something like that together. We will put something like that. It's coming soon. But right now we don't have an example, but you can. So to answer your first part of the question, yes, you can. You can basically put together your own component set. But in the meantime, if you're really interested, I would just recommend to go and, check out maybe this parameter block sort of example in our core and sort of work your way backwards from there until an example is put out by us. But we don't have that yet. Sorry.
So just to make something clear here, we don't have a tutorial on how to do it, but these property packages that we're using here are completely open. You can go look at them and change them. So they are examples in that sense of something you can go and look at, and they show how they are assembled. I'll also make a note that coming in the next IDAES release is a new framework for helping you more easily assemble property packages for common cases.
Yeah.
And we do have cubic equations of state at the moment.
Yeah, which is what I'm showing over here. We support these two right now.
And a follow-up question. So if I use PR equation, will I have to supply the binary interaction parameters and other coefficients, or is it inbuilt for common components?
You have to provide your own.
Yeah, you have to provide your own. So the problem with that, Rahul, is that we are purely open source, and it's very difficult for us to put some maybe mostly proprietary stuff out there in the open. And that's also one reason why for the NRTL itself, even for a simple mixture like benzene toluene, we are doing a parameter estimation with a data set rather than directly putting some parameters for the binary interaction, right? So if you are an end user, yes, we expect you to bring the parameters for the components that you would like to model. So.
Okay, and that completely makes sense. I was just checking. Thanks.
Yeah. Okay, so just quickly to wrap up, you know, this is the results from the bootstrapping analysis, and you can see that, you know, as I told you previously, you don't really see a lot of variation in these 4 runs for the estimated values. And however, this is a super useful feature, and there's some plotting capabilities too. If you go check out the PowerMesh documentation on Pyomos, read the docs. That helps you identify some like confidence regions, and super useful if you're using some real plant data, you know, to estimate some parameters. So with that, I think we're good. So any questions, please feel free to reach out via email on IDAES-support@idaes.org. And please check out our website. We'll be posting this video and any additional materials we'll just send you all an email. So.
Well, thank you, Jaffer. Great job. And thank you, everyone, for staying with us through this whole exercise here. Andrew, thank you for fielding all the questions and bringing them in on the chat room. But especially all the participants, thank you for joining us and for really working through the examples, asking questions, bringing up the issues that come up as you try to do the exercises, and look forward to continuing tomorrow. Anything else to add, Jaffer, before we close?
No, thank you all for your interest, and you know, this was a great turnout. Please join us for the workshop tomorrow. It will be led by Andrew Lee. If you're interested on a flow sheet level, simulation and optimization, we'll be showing how to connect to unit models and stuff. So, you know, please join us tomorrow if you're available.
Yeah, very grateful to have you all with us, and hopefully see you all again tomorrow. Thanks for joining. Have a good day, everyone. Be safe.
Thank you.
Thank you. Bye-bye.